Recording is started. So, what are the plans for today? Well, I wanted to show you that I sent you an email. I had changed the answer to one of the problems I was showing last Wednesday in the PDF that I posted. So I've replaced that PDF with another PDF with the corrected solutions. I wanted to show that to you first. All right. This is it here. All right. So this is that handout that I again showed you last time. So please note that when you do review for your test, that whatever I show you today corrects what was shown last Wednesday. Uh, Actually, I'm kind of glad, if you believe it, kind of glad that I made that mistake because it's a teaching moment for you. And so let me refer to the problem that that changed. This one right here. This is in section 3, chapter 6, number 23, 6.23. This has to do with claims, health insurance claims, I believe, and two people were selected, and either their claim was accepted or not accepted. So there's two options. So we have four different outcomes here. C represents, by the way, that the claim was accepted, and represents the claim is not. So the first outcome, O1, is basically saying that both people, their claims were accepted. O2, it means the first person's claim was accepted, but not the second person's. O3, first person's claim is not accepted, but the second person's is. And the O4 means neither claim was accepted. Now, they give you these probabilities here of each of these four events. Right? This was given in the problem. Notice that the probabilities are not equal to each other, except for O2 and O3 are equal, but the others are not. And then they came up with these additional events. For example, the first one, event A, says event A is at most one patient is covered out of the two, at most. So that means either one patient is covered or neither one of them is covered. That's what they mean, right? So we're excluding O1. So O2, O3, and O4 fit this definition that at most one patient's covered. Now, the way I did it before, and again, I probably did it 1 in the morning, and I wasn't thinking clearly, is I counted the number of cases here, there's 3 of them, and divided by the number of cases in the sample space, and I said the answer was 3/4. But for that to be true, every one of these 4 cases has to be equally likely to occur. Each of these 4 outcomes has to be equally likely to occur. If they're unequally likely, which is the case here, because the probability of O1 is 0.81. And the other 3 cases are much lower, right? 0.09, 0.09, 0.01. So that's not the way I showed it. Obviously, it's not the right way. What you want to do is you take your 3 cases that are true for event A, that is these 3 cases here, and add up their probabilities. What are their probabilities? 0.09 plus 0.09 plus 0.01, which is 0.19. Or the second possibility is, since we're excluding O1, then we could just say 1 minus 0.81, which is also 0.19. If you could think of it as just the sum of those 3 outcomes. And the reason why we can add them is because we're saying either, in this case for event A, either the first person was covered and the second was not, or first person was not covered and the second was, or both people were not covered. One of those 3 cases fits event A. Since we're using the word or, we add. And these are mutually exclusive, right? Mutually exclusive means they cannot occur at the same time. So O2, definitely mutually exclusive from O3 and O4, and same thing for O3 and O4. They cannot occur at the same time, obviously. Can't occur at the same time, so we simply add up their probabilities. B says 2 patients have the same coverage. What are those two possibilities? Well, O1 has the same coverage, which is, well, I think I should have corrected that. Same coverage category. That means they both have this, either they're both covered or they're both not covered. That's really what it meant there. The book explained it better than I did. So O1 and O4 are outcomes for event B because they both have the same coverage status. They're either both covered or they're both not covered. And then in that case, we add up their probabilities, which is 0.81 plus 0.01, which is 0.82. And once again, what I did before was I just simply said there was 2 outcomes and divided by 4 outcomes in the sample space. That's incorrect because once again, the probabilities of each of these outcomes are different. They're the same than what I did before with, the previous solution would have been okay. But in this case here, the probabilities of each of the 4 outcomes are different. So you simply add up the probabilities for the events. P01 plus P04 is 0.82. All right. So I want you to make note of this, that this is the correct solution. And what I did on last Wednesday on video, so you can't say I didn't do it. I did do it. But it is a teaching moment because it tells you that formula where you take the number of outcomes in any event in the numerator and divide by the number of outcomes in the sample space, and that's your probability. That only occurs when the outcomes are equally likely. And in this case, they are not. All right. Any questions about that? Do you see the difference between what I did before and the correct solution now? The book makes it clear if you read the book, but I want to make it clear because if I give you a question like this on the test, which would be a fairly easy question to give, I think most of you will get it correct. But if I do a multiple choice test, one of the answers would be the way I did it incorrectly. All right. So just be careful. Make sure that when you look at the probabilities, that you determine whether they're equal or not equal before you determine how to answer the question. Any questions about that? Everything else on this sheet is fine. All right. Now, if you happen to print out this PDF before I made the correction, then just throw that one out and just print this one. This is the one that's posted now. All right, so I'll stop sharing that. Now there is a quiz today, 3rd quiz on chapter 6. And I did send you an email also telling you that this quiz not only has vocab, some vocab in it, but it also has some short calculations. All right, so Casey, that's okay if you're hearing me, whatever you said there. So short calculations, brief calculations, but the purpose of the calculation is to test to see if you understand the concept. And what are the concepts that you need to understand? Well, the rules of probability, the different rules that we learn. The probability goes from 0 to 1. You should know what a complement of an event is. You should know the addition rule, the general addition rule, the general multiplication rule, and then the special cases where the addition rule with the events being mutually exclusive, and then the multiplication rule when the events are independent. And you should be able to recognize when events are independent, because the probability of one event does not change when given information about the other event. All right. If it does change, that means the 2 events are dependent. Okay. Any questions about that? All right. But these are brief calculations, meaning there's not, a word problem or anything like that. I'm just going to give you some information, and you'll take that information and do a calculation. That's pretty much what I'm referring to. All right. So we started chapter 7 last time. We're going to continue with it. We went through section 7.1. And if I take a look at 7.1 in my textbook, I don't know if you have yours open. 7.1 was basically an introduction to what a random variable is. Remember, a random variable It's a variable that has certain outcomes from a chance experiment. There's the list of outcomes, and each outcome has its corresponding probability. Talk more about that as we proceed. So that was just an introduction to this chapter. That's 7.1, and then 7.2 we started last time, but I'm going to continue with it today. And then 7.3, 7.3 is not going to take very long to do. And if I have time, I'll start 7.4 today, but we'll continue with it on Wednesday, and 7.5 also Wednesday. So by the end of this week, we'll have completed 5 of the 6 sections in chapter 7. And then section 6 of chapter 7 on the normal distribution, we're going to spend 2 sessions on that next week. So just in that section, that's the most important of the 6 sections that we're going to be learning in this book, because it's going to be the basis for what we're going to do for the rest of the course. So we're spending a whole week on section 6 of chapter 7. And once we've completed chapter 7, then we are ready for test number 2, which will cover basically probability and probability distributions. That's chapters 6 and 7. All right. Now there are 2 other sections in chapter 7. Section 7 and section 8, we will not cover those in this course, so those will be skipped. All right. And also I should mention to you that in section 4, that will be possibly covering some of it today. There's a whole part of section 4 we will not cover also. So we'll cover only about a quarter of that section, but I'll tell you about that when we get there. All right, so let's get to section 2. I think it's this one here. This one where we stopped. And probability distributions for discrete random variables. We have to define what a probability distribution is. Okay. All right, hold on 1 second. There we go, that's better. All right, now again, a random variable is a variable that has its possible values, different outcomes, and each outcome has its own probability. So a probability distribution of a random variable is just that. It's just a list of their particular values and their probabilities. For a discrete random variable, that means there's a limited number of values, outcomes, for that random variable. Typically, it's a count. We're counting the number of values. That would be the random variable. And each one of them has a probability. All right. When we get to continuous random variables, the concept's a little different, but we'll get to that in a little bit. So they give an example in the book, in the PowerPoint also. First of all, they want to give you the notation. We talked about this last time. So if the random variable is x, like in algebra, we would pick a letter like x or y to be the variable. In this case, we're calling it x. We say that the possible value of x is 2. We could write it like this, P2, which is the same thing as the probability that x is equal to 2. All right? P5, it means the probability that x is equal to 5. So that's the notation we're going to use. So they give this particular example just to illustrate how we come up with the probability distribution. All right. So we have 4 randomly selected customers at a large appliance store who are purchasing a refrigerator. And there's 2 types. There's either an energy efficient model or there's one that's not. That's less expensive. All right. So we're going to use E for the outcome that the refrigerator is energy efficient, and the letter G for the models that are not energy efficient. And then we're saying, based on long-term information, the probability, if you select somebody at random, the probability that they're going to select an energy efficient model, if they're selecting a refrigerator, is 0.4, And of course, the probability that if it's not energy efficient would be 0.6, obviously, because that's the only other possibility. And the sum of these two probabilities is equal to 1, right? That's the probability of the entire sample space. So the sample space is simply E or G, all right? One of those two, a person's going to choose to purchase, all right? Now, suppose there's 4 people who come into the store, and we want to know what are the different outcomes for those 4 people in terms of selecting a refrigerator. So we're assuming that each of these people are coming into the appliance store to buy a refrigerator. So they're going to buy one of 2 types, energy efficient E or the other type G. Okay, so one possibility, and this is one here, just looking at one possibility, is that the first person comes in and buys an energy efficient refrigerator. The second one comes in and buys the non-energy efficient. Third one does the same, non-energy efficient, and the fourth one buys energy efficient. All right. So this is what the notation is indicating. The first letter is the first person coming in. The second is the second person. Third letter is the third person. Fourth letter is the fourth person coming in. So you can picture there's many possibilities here, but this is one of them. We want to know what's the probability that the 4 customers coming in pick the refrigerators in this order, right? In this particular order, energy efficient first and last, and the 2 middle ones, non-energy efficient. Well, this is a case where this is the multiplication rule, because we are wanting to know what's the probability the first one picks energy efficient and, notice I use the word and, the second one picks non-energy efficient, and the third one picks non-energy efficient, and the fourth one picks energy efficient. Using the word and means multiply. Notice in this case here that if we assume that every person's decision is independent of everybody else's decision, and that we're going to use the multiplication rule assuming independence of these outcomes. So we simply multiply their individual probabilities. We come up with 0.0576. Okay, so that's the probability for this particular event of these 4 people. All right. This is their probability. Now you could picture, in this case, 2 people are selecting energy efficient, but it's the first and the last one. You could picture 2 people picking energy efficient, and maybe it's the first and third people, or maybe it's the last 2 people, whatever. So there's a few possibilities with that, but each one of them, if you multiply the probabilities, you're going to get 0.0576. Okay, same thing, right? It would be the same thing. It doesn't matter in which order these probabilities are in terms of the multiplication, right? The multiplication is exactly the same. Here's a case here where only one person is energy efficient, selecting energy efficient refrigerant. It's the 4th person. Well, the first 3 do not. So this is that probability. Okay. So the random variable in this case is what? Out of the 4 customers, see, the random variable has now changed. We're now coming up with a new random variable, which is the number of energy efficient refrigerators purchased by 4 customers. All right. This is not just one customer anymore. This is 4 of them. So this is a new random variable. X will go from what for this? Well, certainly it's possible that none of the people walking in, none of the 4 people will buy energy efficient refrigerators. So X could be 0. You could have 1 of the 4, 2 of the 4, 3 of the 4, or all 4 of the 4 selecting energy efficient refrigerators. So the random variable X has 5 possible values, starting at 0, then 1, 2, 3, 4. All right. Did I have to tell you that information? No. You should be able to deduce from reading the situation that the random variable has those 5 values and no other values, because X is the number of energy efficient refrigerators purchased by the 4 customers. So you have to think, all right, what's the smallest number of customers that would purchase energy efficient refrigerators? The answer is 0. It's possible none of them did. And what's the maximum number? Well, all 4 do. And any of the whole numbers in between would also be possible. So 0, 1, 2, 3, 4. Those are the 4 values for this random variable. Now, there are 16 possible outcomes if we consider the order, every possible order for each possible outcome. There's 16 of these altogether. And how do we know that? Because there's 4 people and each person can select one of 2 types of refrigerators. So 2 times 2 times 2 times 2 is 16. All right, that's I came up with 16 possible outcomes, and they're all listed here. However, the random variable x is not always different between all of these outcomes. There could be some that share the same value of x, because x is what? The number of energy efficient outcomes out of the 4. Well, certainly G, there's only going to be one of those, right? Only one possible outcome, which has all 4 of them selecting non-energy efficient. And the same thing with the E. There's only one of those. So certainly for this random variable, those are 2 possible outcomes when x is 0, which is G, and when x is 4, which is E. And we obviously can calculate their probabilities, right? Using what? The multiplication rule. However, for all the other ones, there are multiple outcomes that we can add up for that value of x. For example, there are 4 outcomes that have only the one value of E. One of the 4 customers picked an energy efficient outcome. It's either the first one, the second one, the third one, or the fourth one. Each one of those has the same probability, 0.0864. But now we have 4 of them. So what do? We add up these 4, and that will be the probability when x is equal to 1. Same thing with x is equal to 2. For x is equal to 2, there are 6 outcomes that have that. All right, here are the 6 of them. Okay. So each one of them is 0.0576, but now we're going to add the 6 of them together to give you the probability that x is equal to 2. For x is equal to 3, that's 3 energy efficient outcomes out of the 4 customers. Then these are the 4 possible outcomes. 0.0384 is the probability for each one of them, and there's 4 of them, so we add them up, and that would be the value for x. All right. So we will have a summary of that. This is it down here. This table down here, see it? We have our x's from 0 to 4, and we have their probabilities. And notice what the probabilities are. They are the sum of all the outcomes that have that same value of x, right? We add them up, and we get these outcomes here. All right? And you know, these previous slides here, they're telling you pretty much the same thing. So this is the result. This is called a probability distribution table. Make note of that. That'll be on your test. I'm going to be asking questions about this. All right. I give you one that looks like this. All right. X values could be different. Probabilities could be different, but there's a couple of characteristics that makes this a probability distribution table as opposed to just a table of x's and probabilities. What are those requirements? Number 1, each of these individual probabilities are from 0 to 1. You will not see negative numbers. You will not see any numbers greater than 1 for any of these numbers that you see for probabilities. So the probabilities have to be between 0 and 1. Of course, that's the definition of a probability, but if we happen to see numbers down here that are negative or greater than 1, then we know that this whole thing here is not a probability distribution table. It's something else, whatever you want to call it, but it's not a probability distribution table. Now, number 2 is that the sum of these probabilities for probability distribution must add up to 1. If it adds up to less than 1 or greater than 1, this is not a probability distribution table. So those are the two requirements that have to be met. Each of the numbers for the probabilities are each from 0 to 1, and the sum of the probabilities are equal to 1. Both have to be met. Both those requirements have to be met for this to be a probability distribution table. I tend to ask questions on exams about that, just to make sure that you, when you look at one of these things, you know that you have to test to see if it is. If I don't tell you it's a probability distribution table, you have to test using those two requirements to see if it is. If it's not a probability distribution table, you can't make any sort of predictions from it or use it in any way. All right, that's important. Now, in this case here, if I look at this table and I ask the following question, what's the probability that if we select 4 customers at random that walk into the store, what's the probability that less than 2 of them will select an energy efficient refrigerator? So 4 customers walk into the store, they want to buy a refrigerator. What's the probability that they purchase, if they do purchase them, they purchase fewer than 2 of them will purchase an energy efficient refrigerator? So what's the answer to that? How would you do it? This is a very simple question compared to other questions I can ask, but this is sort of the simplest one. What's the probability that fewer than 2 of the 4 people who purchase refrigerators will purchase energy efficient refrigerators? How would you do it? Can somebody speak up and let me know? You don't have to do the math, just tell me what you would do.
Would you add the probability of 0 and the probability of 1?
That's it. Pretty simple. It's a simple thing, isn't it? It really is. Less than 2 means P0 plus or P1. The word or means add. And are they mutually exclusive? Yes. You can't have 0 and 1 occurring at the same time, right? Either you have 0 people out of the 4 purchasing energy efficient refrigerators, or you have 1 out of the 4. So you add up their probabilities, and that's the answer. Okay. So we could, be fancy with that. We could say what's the probability that greater than 2 of the 4 who buy refrigerators buy energy efficient refrigerators, greater than 2. And what would be the answer? Somebody else besides the person who answered just a second ago?
Add 3 and 4.
That's right. P3 plus P4. You just add up those 0.1536 plus 0.0256. We add up those two probabilities, and there's our answer. So pretty easy question. And you will see this on your next test. You'll see it on the final exam. It's always there, and it's always there to give you some nice free points, because it really, literally, if you know what you're doing, this is an easy question to be answering when you have a table like this. It really is. It's an easy question. However, if this is not a probability distribution table, you cannot answer the question. Either one of those questions you can't answer, because if this is not a probability distribution table, these numbers here don't represent probabilities. They don't. They represent, even though you might say that they do, but they don't. Again, each one of these numbers has to be between 0 and 1, and they have to add up to 1. All right? That is required to answer any questions from this table. Otherwise, you can't. The answer is, it's not a probability distribution table. I cannot answer that question. All right? But this one is, because if you add up these 4 probabilities, it does come out to 1. Now, there might be some rounding errors if you do add up the number of probabilities. For example, if you get 0.999 or 1.001, don't say it's not a probability distribution table. It is, because there's probably a rounding error there. But if you add up these 5 supposed probabilities and it comes out to 0.95 or 1.06, it's certainly not a probability distribution table. All right? Okay. Now, how do you interpret these individual probabilities? That's the other thing. So if I say P3 is 0.1536, we could say that the following. if we select a group of 4 customers and they all go and buy refrigerators, the probability that 3 of them purchase the refrigerator, purchase a energy efficient refrigerator, is 0.1536. Or we could say in the long run, all right, if we have groups of 4 people coming into the store, groups of 4 customers, over and over again, purchasing these refrigerators, we would expect 15.36% of these groups to have exactly 3 customers purchasing an energy efficient refrigerator. So that's 2 ways of saying it. Number 1, we could say we randomly select a group of 4. What's the probability that 3 of them select an energy efficient refrigerator? It's 0.1536. Or we could say in the long run, the probability, the percentage of groups of 4 that actually have 3 of them purchasing an energy efficient refrigerator is 15.36% of these groups of 4. So in the long run, that is the percentage of those groups that would have 3 customers purchasing an energy efficient refrigerator. There's 2 possible interpretations there. So get used to that. All right. Again, they're showing you that if I said probability X is greater than or equal to 2, I already showed you an example like that, it would be this probability, and then we add them up using the addition rule with mutually exclusive outcomes. These are mutually exclusive outcomes. So here are your properties again. Every possible probability is between 0 and 1, and the sum, this symbol here, before the P here means sum. That's a Greek symbol, meaning sum. The sum of the probabilities is equal to 1. One way of displaying, by the way, is a histogram. This is a relative frequency histogram where every rectangle represents just one individual value in the distribution. So instead of giving you a table, if I gave you one of these, as long as it's clear what these probabilities are, individual probabilities, as long as it's clear what they are, you could use this to answer questions too. And in this case, it's not clear, is it? Looking at this table, for example, probability of X is equal to 0, you can't tell, you know it's between 0.1 and 0.2, but you don't know what that number is, right? You can't tell. And you certainly can't tell when P is 4 either. So a table is in most cases, is superior to using a histogram. All right, and that is section 2. Now, today we're going to start our quiz at 1:20. So we have 15 minutes to go into the next section, section 3. We should be able to get through section 3 pretty quickly. What we'll do next, go into section 3. So where are you? Section 3. Now, probability distributions for continuous random variables. What we were looking at before, that table that we were looking at, is only for discrete probability distributions. Discrete meaning there are a limited number of possible values for X. That's what it means. What if we have an unlimited number of values for X? For example, for measuring height, weight, time, money. It could be many different outcomes. Unlimited number of outcomes. And so that's the case of what's called a continuous random variable. Okay. Now, as far as this particular section is concerned, you need to know the general idea and maybe some of the simple ideas behind this. This particular section is really a preparation for section 5, or for section 6, when we talk about the normal distribution, the bell-shaped curve. All right, this is in preparation for that. This is giving you some ideas of how we come up with the probabilities. Right? In this case here, because we're dealing with unlimited values, we have to talk about now a function. All right. And again, that name might ring a bell from algebra, the idea of a function. Usually it's some sort of curve, straight line, or a curve. And in the language of probability, when we're dealing with what's called a continuous random variable x, we're going to call that function f of x. And we have a special name for it called a density function. Right? That's what it's called. You don't have to know that much about it, but just a couple properties of it would be excellent to know. All right. And here are the properties. So picture a curve, some sort of curve or shape, something like that you can draw on a graph. And one of the properties of this function is that it's above the x-axis. It's above the x-axis. So it cannot touch or go below the x-axis. Now, it could touch it. I shouldn't say it can't touch it, but it can. But it can't be negative. In other words, it can't be a negative y. So f of x, which is the y value, the height, is always above the x-axis. It can be 0, but it's definitely, it has to be, in most cases, bigger than 0. And the other thing is, if we determined the area under that curve, we drew some shading that showed the area under the curve, it would be equal to 1. And for those of you who have taken calculus, maybe a couple of you have, you know that there are parts of calculus that find the areas under curves, okay? That might sound familiar to you, and you'd used integration as a technique in calculus. Now, for those of you who didn't take calculus, don't need to worry about it. Again, this is just not this information. For those of you taking calculus, you'll understand what area under the curve means. Well, for these particular functions, the area under the curve has to be equal to 1. It's not a density function. It has nothing to do with probability. Okay? It has to be equal to 1. All right. Now, for continuous random variable, what we're going to be talking about is intervals of the values of x. Intervals. That means we're going to have a left endpoint and a right endpoint, and any values in between will be all possible values of the random variable x. Okay, so we're going to talk about it in the terms. This, if you look at 1 here, we're going to look at it like this: that x is between a and b along the number line. X can be any value between a and b, or x could be less than a, or we could say x is greater than b. That's the other possibility too. That's possible too. So here's a curve. These are bell-shaped curves, but they don't have to be. They could be any curves, any shaped curve. Oh, here's 3 here. X is greater than b. So when we want to find the probability that x is between a and b, we're interested in that shaded area between a and b along the x-axis. The shaded area is the area under the curve. Here's your curve. The area under it, it goes down to the x-axis. That area is what we're talking about, and that is a probability for one of these functions. Probability x is less than a would be to the left of a. The probability x is greater than b would be to the right of b. Now, here's the most important thing, one of the most important things to remember about probabilities for continuous random variables. When we talk about them when we talk about probabilities for discrete random variables, we said probability of x is equal to some number, right? We said P2, P3, P4. Well, we don't do that for continuous random variables. The probability that x is equal to a or equal to b or some other number is equal to 0 for a continuous random variable. Okay? Not equal to any value. It's equal to 0. So with probabilities for these continuous random variables, we always calculate probabilities for an interval, either between 2 numbers, for less than the number or greater than the number. These are the 3 possibilities. All right. Any questions about that? So it can get a little confusing because when in the discrete case, we are talking about x is equal to a or x is equal to b, but in the continuous case, X is equal to A is always equal to 0. X is equal to B is always 0. It's always intervals of values that we're talking about for probabilities. Now, they're showing you illustrations of functions where we can find the area under the curve without using calculus, all right? Because most of you have not taken calculus. So what we can do is find the area under the curve and see if it, number one, if it is a density function, and number two, if it is, then we can make probability statements. Now, what is it saying here? It's saying f of x is equal to either 0.5 or 0. When is it equal to 0.5? When x is between 4 and 6. So remember, f of x is the height of the curve, so, or the y value. So it's saying the y value is the same number. It's 0.5 or a half when it's between 4 and 6, and it's equal to 0 any other place. So what does that look like? Well, when it's the same for the same values of x, it's going to look like a horizontal line. So this is exactly what this function is. It's saying between 4 and 6, the height is 0.5, the y is 0.5, and everywhere else it's 0. So there's nothing else beyond 4 and 6 for this curve. It's 0. All right. It's, in other words, it is the x-axis anywhere else. So it's basically this line between 4 and 6, and it has a height of 0.5. Now, if we wanted to find the area under this line, what would we do? We would draw a vertical line from the line down to 4. We draw a vertical line from the line down to 6, and we would create a rectangle. And what is the area of a rectangle? It's the height times the base. So what's the height? 0.5 or a half. What's the base? 2. What's 2 times a half or 2 times 0.5? It's equal to 1. So the area under the curve, area under the full curve here is 1. This is a density curve. It is, because it meets the requirements. It's above the x-axis, which it is. And it is also, the area under it is equal to 1. We didn't need calculus. We just needed to know the area of a rectangle. So this is a density function. Therefore, we can make probability statements. All right. For example, if we wanted to know the probability of, let me see if we can see an example of this. Yeah. What's the probability that x is between 4.5 and 5.5? Well, what is we create this smaller rectangle inside the big rectangle. Okay. And what is the area under that piece of the curve? Well, the base is 1. 5.5 minus 4.5 is 1, and the height is 0.5. What is 1 times 0.5? 0.5. So the probability of having a value of x that's between these two values is 0.5. It's 1/2 probability. Okay? That's how you do it. It's not that hard to figure out. And you have these types of shapes that you're familiar with. And then the probability that x is greater than 5.5 would be from 5.5 to 6. 6 is the maximum value for x. So what's this distance? 0.5. That's the distance from 5.5 to 6. The smaller triangle has a base of 0.5, and it has a height of 0.5. 0.5 times 0.5 is 0.25. The probability that x is greater than 5.5 is 0.25. So by the way, this specific curve is called a uniform probability distribution. Uniform meaning the value of the function stays the same regardless of the value of x. It stays the same for a particular interval. It doesn't change. All right? Uniform probability distribution, that's what it's called. We're not going to use much of that in this course, but you should be familiar with it. Know that it's there. And it's one of the simple ones that anybody could ever draw. And by the way, besides the rectangle, we could also have a function that is a straight line that has a negative slope. picture a straight line running from the y-axis and going down to the x-axis. And what type of, if we find the area under that curve, what type of curve is that? Well, it turns into a triangle, doesn't it? So if we have a function that is a straight line that is negatively sloped and runs from the y-axis down to the x-axis, the area would be a triangle, and we know the area of a triangle is 1/2 the base times the height. So certainly we could also ask probability questions with that. All right. So with common geometric figures, we could have also, of course, have a curve in here that is a quarter of a circle. We know and we may not know, but we may know the function for a quarter circle. The important point here is that if we do know the function, we could find the area under it using formulas. Typically, we don't have that information. So we can only do it for these particular cases. All right, what else? I just have a couple more slides here to show you in here. Remember, with a continuous random variable, I said the probability of x is equal to some value is equal to 0. So in that case, these 4 probabilities are all the same. Probability that x is between A and B would be the same whether we are including A or including B, because the probabilities of x at A and x at B is 0. So it doesn't matter whether you use the equal signs in here or not, because these are 4 probabilities all mean the same. And by the way, when we talk about area to the left, the probability, for example, that x is less than A or less than B, we're talking about what's called a cumulative area. So if you hear that term cumulative area, it means area to the left of that value, the area under the curve to the left of that value. That's what it means. So we'll get to that when we get to our normal curve. So this area here is the cumulative area for when x is 0.5. The cumulative area is the probability that x is less than 0.5. That means to the left of 0.5. It's the entire area to the left of under the curve to the left of 0.5. That's what this probability is referring to when we draw the curve. Okay? Any questions about that? And then finally, one more. We have 1 minute. Well, we have 1:20. This last one here says that if we want to find the probability between 2 values, we take the cumulative area for the value of on the right, and we subtract the cumulative area of the value to the left here, the endpoints. So it's the cumulative area of the right endpoint minus the cumulative area of the left endpoint. That would be this probability. Another way of saying it. All right, we can stop now, and we have our quiz, which is starting right now, 1:20. Give me a thumbs up if you see it, and you have to turn, if your videos work, you have to turn your videos on now. Hopefully you're going to be close to the point where, for those of you who have broken videos or needed new videos, that you have them. If we have a test coming up, and please, it will be required to have a video on, unless there's an emergency. You have to have a video on when you're being tested. So please turn your videos on now, or send me a chat saying you still don't have it, but please, you need to have it soon. All right, because we're halfway through the course, and this is a requirement for this type of course that when you're taking an exam on Zoom, that you have a video, active working video, so professors can see you, not just me, any professor. All right, so anyway, the quiz is available. Go ahead and start it, and good luck. Again, send me a chat if you have a question. Somebody send me a chat. All right. So yeah. Now, please, if you're driving, please, if you can arrange it so that you're behind and not driving when you're taking this class, that would be the best thing. All right. Your test schedule should not be so tight where you're driving while you're taking this class. You're going to have a tough time taking your exam when you're driving. All right. Please have these videos fixed before the next test. It's in a couple of weeks. All right. So just know that. Don't let it slide. All right. Thank you. All right, I'll turn off my video now. Turn off recording.